All right, so we're entering some territory which I really like. So close all these things all the way up. Everybody have a look. So we're getting into kind of applications of calculus. And so I want to, this to me is a really fun part of calculus. The good news for you is that the sections we're entering, like I have given you guys some really hard stuff with chain rule stuff. Like, I mean, when I show this stuff to like other calculus teachers in the state, they're just like, oh my God, you do this to your high school students, or they're just, because it is really pretty hard stuff. But if you can do it now, this is going to be so easy next year. Because I mean, if you can do, these are kind of bedrock foundational things. If you can do the complex chain rule problems, man, calculus is going to be so easy. So I'm kind of doing this at the expense of, there'll be a few little minor topics that otherwise I would cover this year that we would just do kind of at a surface level. My philosophy is always, I'd rather go really deep on the important stuff, and then you can always fill in the blanks in college with the other things. Yeah.
In the application of this stuff, are we going to mess around with any circular inertia?
Circular inertia?
Rotational inertia.
I mean, we could.
That's what we're doing in physics. That's why I was asking.
Rotational inertia? I mean, yeah.
We're not doing. No, Cooper said we're not doing rotational inertia. We did that in college.
Rotational inertia, and we could take a day and talk about that stuff a little bit too, because there's some really good analogies that help you understand that. It's like if you compare rotational inertia to linear inertia, like I always talk in physics about linear land and Angevin, and like you can make all these, you guys probably do the same thing, right? You can make these straight comparisons between angular equivalents of linear variables and linear quantities, and then it gets pretty easy to understand it. And there's a direct, I mean, you can like take all these, like all your kinematics equations, even dynamics equations in physics, and you can say, okay, if this is what it is in linear land, that's what it is when you're talking about linear physics, translational physics, then.
He taught us as position space versus velocity space.
I mean, right, I mean, you can, but what I'm saying is something different than that even. What I'm saying is that you can make these analogous, you can, without even knowing them, you can come up with what all the analogous quantities and relationships are for angular physics, because it's exactly parallel to what happens in translational physics.
Yeah.
Right. And I'm sure you did the same thing. But
that's exactly what we did.
Yeah.
So what about driving the rotational inertia from the
floor? Well, that requires some calculus that we won't have until maybe the end of the year, if we even get there.
Okay.
Yeah. But it's we can at least, remind me later on, we can at least talk about how you would do it if we don't have it. Yeah. Okay, so for today though, let's look at some things like this, because this is an application, kind of a biomedical application, and this is something that you would deal with if you were going to medical school. If you were going to be looking at things like, if you were, what's that called when you do they put you on a table and the blood, no, when your heart pumps and blood goes pulsing through your vasculature, it actually, there's going to be a transfer momentum between the blood and your body. You can actually see that your body moves a little bit on the table. So what do they call that? There's a name for that. Something, I can't think of what it is. But it's actually a form of, it's a diagnostic tool in medicine, right? It has to do with some calculus here, right? It has to do with the relationship between, how is the blood flowing at a really specific level in the arteries and veins. Okay, so let's take a look at this. The speed of blood that is r centimeters from the center of an artery is modeled like this, right? Where S stands for speed. Capital R is the radius of the artery, so that's a constant, we'll say, right? Little r is the variable, right? Because we're measuring, like if we were to look at a cross-section of the artery, this is what we're talking about. If this is a cross-section of the artery, so there's the artery kind of snaking away, and we just cut through it, right? So we're looking at the distance from the center of the artery out to some level. Like that would be one value of r right there, that distance. A little r, not big r. Right, so that would be one value of r. A different value of r would be like clear out here, or smaller would be in there, right? So what you notice is that the speed is equal to some constant, c is just some constant, times big R squared minus little r squared. So little r, what's the domain going to be? We're going to start talking about, like, look at the functional analysis here, real analysis. What's the domain going to be for the only variable, which is little r? And we probably should write this as speed as a function of radius equals c r squared minus little r squared, right? The only variable is the radius as measured from the center of the artery. So what's the domain going to be?
0.
What are the values of r that would make sense as input values?
Greater than equal to 0, less than or equal to big R.
Okay, so we could go like 0 out to r, right? So at the wall of the vessel, the value would be capital R, wouldn't it? So what is, let's just do it, just quickly evaluate this and just make sense of this. So S of big R would equal what? If I plug in capital R for little r, if I evaluate this function at capital R, what am I going to get back? 0. Everybody agree? I'm going to get r squared minus r squared, right? Okay, that makes sense. That's, in physics, we'd call that laminar flow, right? So at the wall of the vessel or the tube, the velocity of the fluid is going to go to 0 because it interacts with the wall, right? As you get closer to the center, you can probably see if we graph this, where's the speed going to be biggest? The center. Makes sense, right? Okay, so suppose a drug is administered and the artery begins to dilate at a rate of the capital R dt. So now we're actually going to dilate the vessel, so it's going to get bigger, right? At a constant distance, so they're flipping this around, at a constant distance r, so now little r becomes the constant. We're going to say for some distance from the center of the artery, find the rate at which capital S changes with respect to t. Okay? How would we, you guys actually have the tools to do this right now. I would start with this equation, and what am I going to do to get ds dt? Because that's what we're looking for, isn't it? We're trying to find the rate at which S changes with respect to, find the rate at which S changes with respect to t. Well, that's just the definition of a derivative, right? The rate of change is a derivative. The rate of change of S with respect to t is just going to be ds dt, right? So how could I do that? And that's the topic of the day. So if you get this right now, I can just drop my pen and walk out the door, and you guys can, no, but we've got to do a little more to the topic. But that's the topic. This is, how do we do this? And you kind of already know, because I've already alluded to this before. What would I do with my, start with my parent equation, which is, write this down again. So S equals C times R squared minus R squared. And I want to come up with ds dt.
Let's see, so what was it's dilating in seconds?
And so it gives us some values, doesn't it? It's going to tell us, when we're all done with this, doing the calculus part, it gives us some values to plug in. It tells us the value of the constant is that. The value of the radius, we're looking when the value of the radius is equal to this specifically. We've dilated it to, what is that, 1.2 centimeters radius. And the rate at which the radius is changing, they're even telling us, is 10 to the negative 5. Okay. But if we just do the calculus part of it, this is what we're getting at for today, is how do we get to here from here? Okay, take the derivative, but you're right. You're right. But what we're used to doing here is we would be used to saying something like this would have made perfect sense. If I had given you this function right here and I had said, what's S prime of R? That would have been ds d little r, for example, right? That makes sense. That makes sense to you guys probably, right? Because these are just constants and there's my variable, right? But what I'm asking you to do here is a little different. I'm asking you to calculate the derivative of s with respect to t. There are no t's in that equation.
Takes, yes.
So what do we do? And that's possibly part of something we could do here. And then dr over dt. So you're getting at, and you shouldn't know the answer to this, and we haven't taught you this, but literally what you can do, there's no reason why we can't just differentiate with respect to any variable we want to, right? I mean, we can take a derivative with respect to anything, and I'm going to give you a couple examples. Like if we were going to do this, and this is flirting with a concept that you're going to talk much more about, not probably even next year in calculus, but like the following years of college calculus, when you do the partial derivatives, or you're doing derivatives, you have multiple variables, but the concept is really simple. So if we have something like, let's say, y is equal to x times, let's not make it y, let's make it w. You'll see. Let's make it w equals x times y times z. If I want to calculate dw dz, what's the answer? Well, it's literally just xy times 1, because I'm only differentiating with respect to z. Now, there are some other little caveats there that I haven't discussed, but assuming these are all orthogonal, and they're unrelated, they're mutually exclusive functions and all, but there's some other things we'll talk about more in college. But we could differentiate this with respect to, to just to z. I could do something like this. I could say, let's let z equal x times y, and let's find the derivative of z with respect to t. I can do that. The derivative of z with respect to t is just equal to the derivative of x times y with respect to t. Well, that's a product, right? So I got to use the product rule. So I'm going to do the first times the derivative of the second. But when I differentiate the second, I'm not differentiating with respect to y. I'm just differentiating with respect to t. So I get x times dy dt plus y times dx dt. And you might ask, why in the world would you do that? I just get a bunch of extra derivatives in there, and but maybe that's what we want to do. Maybe we want to know, how is this function z changing with time? To answer that question, I would also have to know then, well, what values am I plugging in for x and y, and what values am I plugging in for dy dt and dx dt? I'd have to have some additional information to be able to actually make use of this derivative and evaluate it, right? But we can do the same kind of thing with this. I could differentiate this whole thing with respect to t, and the derivative of s with respect to t is just ds dt. What about this side? Well, that's a constant, right? So I can leave that out front. And then this is actually a constant for part 2, isn't it? Yeah. Right? This is the thing that's changing. So what's the derivative of r squared with respect to t? Well, the derivative of hand squared is just 2 times hand times the derivative of what's inside. Well, what's the derivative of r? It'd be 1 if I was differentiating with respect to r. But if I'm differentiating with respect to t, it's dr dt, right? Minus, well, that's a constant, so the derivative of that with respect to anything is 0. So my answer would just be 2 times c times r times dr dt is the answer. And I have all that stuff, actually. I could go up here and plug that in. It tells me what c is, it tells me what r is, and it tells me what dr dt is. So I could plug all those values in and get a numerical answer for this thing. Okay? So, is that crystal clear? Probably not. That's my introduction. That'll make much more sense in a few days, right? I want to start with a different way of doing this, though. This is really cool. I really like this, teaching this stuff. This is a really fun thing. So if we want to start with something like y equals x squared, I just go here. Let's find dy dx. Sorry, I got the back. Y equals x squared. Let's find dy dx. What is that?
2x.
Piece of cake, right? So we know y prime just equals 2x. End of story, right? And we can use that to our advantage. I mean, this is all going to be very familiar to you. If we want to evaluate this function, let's say we want to do something like find the equation of a tangent line when x equals 2, okay? Or x equals 3, how about? So all we would have to do then, the slope of the tangent line would be what?
6.
Right? And my point of tangency would be 3 what? Okay, and so we get the tangent line, we would just end up with this curve. I'm going to go over 3 and up 9, right, so clear up there. And at that point right there, I'm going to get a line given to me by the equation y minus 9 equals 6 times x minus 3, right? That's the equation of that line. I haven't simplified it, but that's fine. If I graph that, that's what I'm going to get, right? Okay, what about this one, though? Our last one was easy. And I'll tell you why this was easy, too. I'll put one more word on this. This was easy because this was an example of explicit differentiation. It's explicit differentiation because we have an explicit function of x. We're differentiating a function that is written in terms of the variable that we're differentiating with respect to. We're differentiating with respect to x, and conveniently we have a function of x. That's what we've always dealt with in the past, all year, right? This is different.
So it'd be 2y dx.
Okay, so let's do this the old-fashioned way first. Prior to today, the only way you would have thought to do this would have been to make this an explicit function and then differentiate it, right? So let's do that. So if we solve this thing for y, what do we get?
Y equals the square root of x.
Okay, not quite though. Close.
Minus.
Say it again.
Plus
Plus or minus. Right, plus or minus the square root of x. Now, let's first of all remember, let's kind of go back to Honors Algebra 2 for a second. I know that we talked about this, because I purposely do this in Honors Algebra 2, so I know we talked about this, just not quite at this level, right? But we did go through this stuff when we were talking about inverse functions, right? Whether something is an inverse relation, whether a relation has an inverse that's a function or not. And this is one example we use for sure. If I graph this, what does it look like?
That's kind of like a parabola. It's rotated 90 degrees clockwise.
Okay, so it's going to be a sideways parabola, isn't it?
Yes.
Right? So it's going to look like this.
Yeah.
And the top one, that's the function y equals the square root of x, and the bottom one is just a reflected version of that minus the square root of x, right? And so it makes sense then, the math gods in their wisdom, they give us a plus or minus here so we can treat each of these separately. So each one of them on its own acts like a function, right? Together they're not, but if I say plus or minus, then each one individually is, right? So we could go through this then, and we could take each of those two, and let's do that. Let's take one function is going to be y equals the square root of x, and then over here we'll take y equals minus the square root of x, and we're just going to come up with the derivative by dealing with both of them. Inconveniently, we ended up with two of them, so we got to differentiate both of them separately. So we know this. What's the derivative of the square root of x?
1 over the square root of x.
Okay, we've done that a bunch. How about this one?
Negative 1 over 2 square root of x.
Okay. It would sure be nice if we could write those in terms of a single answer instead of having just
Plus
one
or minus
separate.
1 over 2 square.
Yeah, but plus or minus is 2 because I said the word or. Give you a little hint. What if I just rewrote this?
Y squared equals 4 over x.
How can I merge those into just one convenient answer?
Square the side, each side.
Gosh, if only there were a way.
Can't you just square each side?
No, I can't do that, because if I square each side, I'm changing things.
What about absolute value? Y squared equals
Think about, I guess what I want to do is maybe, I got to scoot up a little more. What I really want to do is I really wanted to put boxes around those.
Y squared equals this.
So is there a way I could write this y prime and that y prime so the same so that the same expression took care of both of those possibilities?
1 over this. They're both equal to y prime. Can you just set the y primes equal to each other?
No, can't do that.
Things aren't healthy.
I just did a little substitution here. On the left-hand side, what was y defined as? In other words, what was y equal to? Square root of x. On the right side, what was y equal to? Negative the square root of x. So how could I write both those answers?
1 over 2y.
Ah, okay. Would you agree? And then I could write both of those answers using one simple expression takes care of everything, right? Well, that's exactly what we get if we just approach this a little bit differently, right? What if we were to, I want to just do this. If I just start with y squared equals x, and instead of breaking this into two explicit functions, let's do what we talked about at the start of the period. Let's just differentiate with respect to whatever we want to. What are we trying to get out of this? We were solving for y prime, right? We were looking for dy dx. Everybody agree? So why wouldn't I just differentiate with respect to x instead of having to solve? See what I'm saying? As it stands right now, I'm just going to differentiate both sides of this equation with respect to x. So to get from here to the next step, differentiate both sides with respect to x, which is what we call implicit. Implicit differentiation. And we can distinguish that from explicit differentiation because our function here, y, is not defined explicitly in terms of x. It's not y equals some function of x. I've got some function that involves y also, right? Got a y squared. But what happens if we do that? On the left side, by the chain rule, if I differentiate with respect to x, what am I going to get? And I'm going to write it this way. So the derivative with respect to x of y squared equals the derivative with respect to x. In an algebraic sense, I'm treating both sides of the equation the same, so it's got to be okay, right? Well, what do I get on the right side? The answer is easy. What's the derivative of x with respect to x? 1. I just get dx over dx, which those cancel. It's another way of justifying that. What about the left side, though? How many links in the chain are there here? Yeah, I've got the derivative of tan squared, which is what?
2y and then dy.
Aha. 2y times the derivative of y with respect to x is a y prime. Everybody see that? Okay, well, my goal was to solve for dy dx, which is y prime, so what's the only algebraic step to get that y prime by itself? Divide by 2y. And what do you know? I get y prime equals 1 over 2y.
That makes more sense than
We've seen that before, haven't we? Right?
I still don't get that.
But that's a bad way to do it. And sometimes, why is this a bad way? It's a bad way because it was harder to do, and oftentimes you can't even do it, right? There are many cases in math where you cannot explicitly solve for a variable. That we could have something where we got multiple terms with y's in them, and they're so, you know, tangled up with some other variables that it's literally impossible to isolate the y. But you can always do this. You can always implicitly differentiate. So this is a hugely powerful tool for us in calculus, right? Now, what if we want to do something like this? Find the tangent line at x equals 4. Okay? Well, we need to get a derivative, but we're just going to implicitly differentiate to get our derivative. We already did this one, right? And we already got the result when all the dust settled, that y prime equals 1 over 2y, right? Okay? So if we want to evaluate this function at x equals 4, well, first of all, we got to know what's the point of tangency when x equals 4. So if I solve this equation, if I let x equal 4, look what we get. We get the equation y squared equals 4, and we got to solve for y. What do I get when I solve for y? Aha, so y equals plus or minus 2. Makes sense though, doesn't it? Because if you look at this graph, which we've already done once, if I graph this relation, it's not a function, right? It's not a function of x, it's a function of y, but it's not a function of x. If I graph that relation, we already said, it looks like that. Well, if I go over here to x equals 4, sure enough, there are going to be 2 places on that curve that have x-coordinates of 4. I'm going to get the place right here, which is at 4, 2, and I'm going to get the place right there, which is at 4, negative 2. So there's more than one tangent line here, right? When I differentiate this thing, look what my result was, okay? So if I want to know what this tangent line is, well then I'm going to have to use this y value and not that y value, right? So here, the slope of the tangent line, if I apply my derivative function, what's that give me? Well, y prime is going to equal 1 over 2 times 2, which is 1/4, right? So this tangent line here is going to have a slope of 1/4, while this tangent line down here,
Negative 1/4?
yeah, if I plug in a y value of negative 2, I'm going to get y prime equals 1 over 2 times negative 2, right? Get the idea? Okay. How much time we got? Oh, okay. So we're going to finish this thing. This is good. I like this. Okay. Well, that's the example. I'll come back to that. Yeah, we'll come back. We'll come back to that one. So I'm going to give you another example of the problem. So what if we want to do something like this then? What if we have, like, let's say 2x squared plus 3x y squared minus 2x squared y plus 4y cubed equals 7. And I want to find y prime. I would double dog dare you to solve that for y. And if somebody told me to solve that for y, I would double jump in the lake. I wouldn't want to do that. That'd take too much time. It wouldn't be something I'd ever want to try doing. It would be really difficult. So you wouldn't want to solve this you would not want to try to isolate y in terms of x here. So if we want to find y prime, what do we need to do instead? Implicitly differentiate with respect to x, right? So what's that going to do? If we implicitly differentiate, what's that going to give me? What's this first term going to give me if I differentiate with respect to x? That's an easy one, right? 4x plus, this one's going to be a little tougher, right?
6x dx dy.
Okay, so, well, but no, what were you going to say? Katie, what do I have to do with that? But if I'm gonna differentiate, but I've got a product here, don't I? Right, so I'd have to use product rule on this. So I'm gonna end up with 3 times, this is an easy product rule, right? I've got the product of x times y squared. So I'm gonna get an x times, what's the derivative of y squared with respect to x? 2y, we'll call it y prime, right? Plus y squared. Plus, yeah, now we've got a y squared times the derivative of x, which is just 1, right? We agree? Okay. Minus, and I made it kind of a tough one, didn't I? 2 times another product rule 1. So now I'm going to have x squared times the derivative of y, which is what? Y prime. Plus y times the derivative of x squared, which is 2x, right? Good. And then plus the derivative of 4y cubed. What's that? 12y squared y prime equals the derivative of 7, which is 0. Well, I want my y prime, I want this all the same color. Okay? Question?
So you basically just treated it like a chain rule until you get to y, and then you just change it to y prime.
Yeah, exactly. Yeah, and that's really all it is, isn't it? If I'm differentiating, like let's take this last term. How many layers are there to that derivative? 2. How many were there to this one? 1, because I'm differentiating with respect to x. See the difference? Okay. So now let's quickly, I just want to finish this problem, and then and then it's good for today. Thank you. So I'm going to distribute the 3 and distribute the -2, and let's simplify while we're doing that. So 4x, help me out here. So what's that term going to be? Plus 3 times 2 is 6x y squared. No, that's just a y times a y, right? Oh, that's supposed to be a y prime. Never mind.
Yeah.
You're right. Y prime. My mistake. My mistake. I did. You're right. I don't know where the prime went.
Yeah, it's not erasing on you, erasing the
Oh, okay. I got you. That was my mistake. So 6x y prime.
plus 3y squared.
Okay, plus 3y squared minus 2x squared y prime plus, or minus,
Minus 4xy.
yeah, minus 4x times y plus 12y squared y prime equals 0. Now I want you to notice here, this might look like there's still a lot of work to do, but there's very little. If I'm solving for y prime, what's really helpful? It equals 0, sure. But notice all these terms. What do you notice about when y prime shows up? Is y prime ever to like another power here or something? No, it's always linear, right? And not all the terms have y primes in them, but if I think about the steps you would go through if you wanted to isolate y prime, see if this makes sense. Wouldn't you want to maybe collect all the y prime terms on the left side of the equation, push all the non-y prime terms to the other side, right? And I'll write it out this time. But I'm going to challenge you guys, and I think you can do this. I think after you've done the problems like this a couple times, you can literally just write the answer down in one step. You can do this in your head. Well, I'll go through the steps now, but you'll see why. It's really not as hard as it looks. So sort of like intermediate step 1 would just be, let's collect all the y prime terms on this side. So that's this term, and this term, right? So we got 6xy, y prime, minus 2x squared y prime plus 12y squared y prime equals, I'm going to chase that term to the other side. I'm going to put this one there first because it's going to end up being positive, right? So when we add that term to the other side, we get a 4xy. So so that one's gone. We're going to subtract 4x, so that one's gone. And we're going to subtract a 3y squared, so now that one's gone, right? What are the last two steps to solve for y prime? Factor out of y prime. So if we included it, the next step would just be y prime times 6xy minus 2x squared plus 12y squared equals that stuff. And then last step?
Divide by the other stuff.
Yeah, just divide both sides by that factor. There's a lot of writing. Maybe carpal tunnel teaching calculus.
You could save yourself some writing books. Right.
There it is.
Right.
There's my answer. Okay, so we probably, do you see how we actually could have gotten to that answer even from up here? Right, when you're doing implicit differentiation. Because you can see that all the non-y prime terms are just going to get moved to the other side, so the signs change, there they are. And then we're just going to divide by whatever the coefficients of y prime, which is just all the other stuff that's on the left side then, right? After I factor out the y prime, right?
You could have done the same thing as uy dx, right? You
Sure.
just wrote it in a different version.
Yeah.
Okay.
So, and then, now if I wanted to evaluate this derivative somewhere, to actually use it to find like a slope, what would I need to have in order to calculate a slope? Values of x and y, wouldn't I? Because presumably this might be something that overlaps vertically quite a bit, right? Could be. Okay? Make sense? Okay, it's a lot of stuff. Stop.
Obviously, it's complex.